Cool. Thanks everyone for coming. I'm going to be talking to you today about a system for GPS analysis that we built called Atlantes. We built this system for Skylight, which is one of the projects at AIT that's focused on maritime intelligence and specifically building AI systems for global monitoring of illegal, unregulated, and underreported fishing. Right here you can see the Skylight platform where we surface tons of different kinds of artificial intelligence-based events and other types of events to our users to help them with their operational decision-making. Our program is focused on delivering these insights to the partners who need them most, and we work really closely with those partners so that our technology can be on the ground and making impact. So how does Skylight use machine learning? Basically, there's two core questions that Skylight users want to be able to answer. They want to know what behavior occurs in their waters, and they want to know where vessels are in their waters. So the first way we do that is by taking in these GPS messages and doing modeling and analysis based off of those. And the second is by doing satellite imagery-based vessel detection. The focus of our talk today is going to be on the models that take in these GPS sequences. Right here, we have a global view of GPS data at sea. So there's over 20 billion plus messages in a year, and you can see some really intricate and not so intricate patterns such as shipping lanes that become much clearer when you get this global view. Cool, so first a primer, what is AIS? It is a GPS system for boats, and what it does is basically allows boats to not have collisions at sea. So initially, if boats were in like fog or in a storm or something, they would transmit their messages so other boats can know where they are. At some point, people put satellites up in the sky that could collect this data at scale, and that's how we're able to get real-time streams of what every vessel in the world is doing who is sharing their GPS messages. So what makes AIS data unique? Well, the first thing is the transmissions are really irregular. When we actually get messages from a boat is dictated by how close it is to either a terrestrial receiver or a satellite in the sky. So we often get these somewhat sparse messages that are not at regular time intervals and things like this. Also, the metadata we get alongside this vessel that might say something like what type of boat is transmitting this or what's the name of this boat is only available sometimes. Boats don't always transmit this. They sometimes just transmit like where they are. So you get a trajectory where you don't know where it's from or things like this. Cool. So let's dive a little deeper into what exactly do these trajectories look like. So the first thing a vessel could be doing is being moored, which is basically it stays in place. You can see there, it means all the GPS messages are in the same place. Another thing a vessel can do is be anchored. It drops anchors, it ends up drifting in a circle. So pretty clear what it's doing. Another thing a vessel could do, it could go straight. It's transiting, right? Vessel's going one place to another. The behavior is very clear. Another thing is fishing. So fishing activity might look like a vessel goes, drops its gear out, and then drives back over the same path and picks up its gear, and then it leaves. So modeling AIS is really easy. Everything is either stopped, it's going in a circle, it's going straight, or we're fishing, right? But in reality, this is far from the truth of what vessels are actually doing at sea. Vessels can do so many different things for so many different reasons. On the left, we have an image of a vessel kind of transiting back over itself in an area, potentially waiting for something or looking for something. And we don't have information on why these captains are doing these things. We just get this movement pattern, and we have to be able to distinguish from this movement pattern what's really going on. Additionally, like anchored behavior, although it might seem like it's always going to be in a perfect circle, in reality, with the sparsity of the messages, you're not always going to get that perfect circle, and you might get this like weird jaggedy movement pattern that seems like it could just be moving around in like a small area, but in reality, it's actually anchoring. And then transiting behavior also, that can look like a lot like fishing. So what we're trying to do when we model AIS data is characterize every single vessel or object in the water in near real time. We want to be able to provide this information to our users in a way that they can make operational decisions. So what do Skylight users want to know from AIS data? There's kind of two core questions that we want to be able to answer for them with this system. So the first is what entity is transmitting the GPS messages? And what this means is the GPS message coming from a buoy, so a floating object in the sea with a transmitter attached to it? A lot of times fishermen will attach these to their buoys to keep track of them. But from our perspective, if it's not saying what it is, we don't know the difference between that and the vessel. And when someone's going out, we can't tell them that, oh, there's a vessel fishing there, and then they go out there and it's actually just a buoy. So we want to have a stateful understanding of if an AIS transmission comes from a buoy or a vessel. And the second thing is we want to know what activity is a vessel doing at a given point in time. And this is so we can provide real-time fishing events to our users so they can look in their area and be like, okay, what's happening right now? What decisions can I make based on this? So kind of throughout the slide, this presentation, I'll be talking about two different models, one for entity and one for activity, and I kind of demarcate them with these buoy and fish icons to help us keep track of what we're talking about. All right, so first, what is the entity classification task? So given a historical sequence of end messages, we want to predict if the messages came from a buoy or vessel. So we'll pass in this track, and then we'll get a binary classification of like, is it a buoy or is it a vessel? We will basically just pick some portion of this vessel's history that's sufficiently dense that we can actually see what it's doing and it captures its like regular activities. So we wouldn't use like the vessel was just at port for a month. We would not use that segment for classification because there's no real signal there. So I have a question for you guys. Which trajectory do you think is a buoy? Any guesses?
Right.
Right? Well, in reality, it's the left. It can be really, really hard to tell for anyone except for an expert which is which. There's a lot of intricacies in how exactly it might be drifting that might point us off that it's not how a human would orient a boat to drift it or other things like that. Also, as well as the rate of sparsity, because there is a human turning on and off this thing. And one of the things that makes this particularly challenging is a lot of times when vessels go and pick up their buoy, they don't turn off the transmitter right away. So you'll get like, you can see here, there's if orange is like faster movement, there's portions of the track where it's moving like a vessel would, but the overall behavior indicates it's buoys because you have these patterns of being dropped off, it floating around and being picked up. But whether it's actually turned off quickly or not is highly variable. The next task is the activity classification task, and this is a basic seek to class task where given a sequence of NAIS messages, we want to predict the activity class of the nth message. So we have this trajectory here. We want to be able to say what is happening right there, and the idea is that as soon as we get that last message, take that trajectory and say what's happening right now, so we can constantly be updating our worldview of what's going on in the ocean. The four classes we're going to focus on for this are fishing, transiting, moored, and anchored. It's important to note that transiting is a very, very broad class that includes tons of different subtypes of activity that weren't relevant at this point for us to demarcate and go into specifically. So transiting includes like all types of ways a vessel could move at sea that aren't fishing. So next question is, which activity is fishing behavior? Does anybody have any ideas about which one this could be?
Left.
Left? That's great. Yeah, Mike. So fishing is on the left. You can see though that there's very similar drifting and going back and drifting patterns in both a fishing and a non-fishing vessel. So kind of being able to look at the past data for the track and really understanding like why would a vessel drift in this way versus that way is important for the model to be able to understand what is fishing and what is not. So all these models learn from GPS data directly. We just use a position, a speed, the direction it's going, and the time it was doing this. And because these models were built from raw data, they're applicable to many other GPS-based sequence tasks with relatively little transition that needs to be made. So in the rest of the talk, I'm going to talk about the Atlantes system. I'm going to focus on three things. First, how we built these data sets. Second, the modeling that actually went into using these data sets to produce a model, and then how we optimize for high performance in production, right? We need these models to be performant at a global scale, and there's a lot of different steps we went into iterating and getting the models to a place where they're providing useful insights for our users. Cool, so first I'm gonna talk about building the training data sets. So for the entity data set, we were able to find basically static metadata that was able to communicate that this entity was a buoy or a vessel, and we were able to find it for a sufficient number of buoys. Like for example, it might have buoy in the name, or we might be able to find from some other source that it was like that specific messages are coming from a piece of fishing gear, and this was able to provide us with enough labels to train a model. Unfortunately for the activity data set, there isn't reliable metadata on like what a vessel is doing at any given point. So we needed to enlist experts who are able to really accurately tell what the vessels are doing. And the other challenge that we had when building this is previously there was no good GPS annotation platform. The old way of doing it for other people who had built fishing models was some combination of QGIS, CSVs, emailing stuff back and forth, and you're not going to be able to build a large high quality data set doing that. So the first thing that the Skylight team did was build a custom annotation platform where the experts are able to look at the GPS sequences with all the context they need to make an accurate decision. So they might want to look at how fast the vessel is going at a different point, what time of day is it doing these movements, and be able to toggle in and out so that they can easily mark different parts of the trajectory with specific activities. We had them make their labels at a message level, so we were able to tell that when is an activity starting and when is an activity stopping. So we would have contrasting labels of like, okay, even though it has pretty similar context, at this point we know it's this activity, but this point, like 100 messages later, that might share a lot of the same context is actually a different activity. So we ended up with these labels that basically take an entire track for an entire month, and we had them say, okay, what's it doing here, 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 and circle these parts. And what we ended is basically just like a sequence of what entire vessels have done over the course of an entire month. So when we are picking what tracks we actually want to get labeled, we have three things that we focus on. First, we want the model to be able to perform well at a global scale, so our data needs to be globally, geographically distributed. Second, we want the model to be able to predict fishing events across all different fishing gear types. So depending on what you're fishing for, you might use a different way, such as purse seining or trawling or gill netting, which basically affects like how you're moving your net or pots through the water, and that will form different movement patterns. And we want to be able to predict fishing events for all these types. And the second is a lot of fishing stuff is really seasonal across the world. So we want to make sure we do well across the entire year. So we need to make sure that we have data across the entire year. So what we did is basically a stratified sampling strategy where we first had basically created these like really high resolution maps for every month for 2 years. And with these high resolution maps, experts can actually go in and like create polygons around fishing areas for all types of fishing. So we had them make these polygons, and we did a stratified sample across months and across all these fishing areas for the course of 2 years. And we additionally sampled a bunch of data outside of those as well, just to kind of catch whatever other parts of the distribution we might be missing. So after we collected an initial amount of this data, we wanted to make sure that the rest of the annotations we collected were as effective as possible. And because we need experts to do this, it can be expensive to just do as much as you want. You can't just hire anyone to do this. So we wanted to make sure we were getting annotations very effectively. The way we did this is we trained a model on the first 4,000 track months and basically applied this model across like tons of data from all these different regions in our stratified sampling approach. And we focused on picking examples where either we had fishing as the top class for some portion of the trajectory, but it was pretty low probability, or fishing was the second highest class and it was relatively high. So if like we had like a 40% confidence that it was fishing, we might prioritize that track over a track where we were like 90% sure it was fishing. So the final data set that we got was about 7,500 track months across both 2022 and 2023. Here you can see the global distribution of that data, and we ended up with about like 1.5 million total labels. It's important to recognize that the labels that we actually use are downsampled from the annotator's total annotations, because there's some cases where it just is going to make training slower and all this type of stuff, because like if a vessel's doing the same thing, like it's moored, or it's transiting, we don't need to, and it's like only like a couple minutes apart, we don't need to feed those because they're essentially the same label to the model. So we downsampled it to cover changes in activities and things like this, so that we had effective training label, but we weren't like basically repeating tons of examples across the data set. Cool, so how did we model this data? So the architecture for both the activity and the entity model were the same, only the task-based output head was different. The architecture that we empirically found to work the best was having this initial layer called a continuous point embedding. that basically allows you to deal with the fact that you have irregular spatial and temporal sequences, and then having a 1D CNN that goes into transformer layers. We tried a lot of variations of this, and this is what we found trained the most efficiently and gave the highest performance. But other variations do work well, and you can do it. Our goal was to find something that worked well enough that we could train it and really focus on the data and the other parts of improving the model. So it's definitely not the most optimal possible, but we found it was pretty strong for our use case. Because the model is only under 5 million parameters, training was pretty fast, even on a substantial number of tracks. So like for every label, you're passing in about 2,000 messages. And so that was like the main bottleneck of the training. The actual forward pass was pretty slow. Was pretty fast. All right, so to give you guys a little better idea of how the continuous point embedding works, is what we do is at a specific point, we take some window around it and we try to figure out, okay, compared to these points, how far did it move in both space and time? So like if we're at this point, we'd say like, okay, it moved like 40 meters if we had 10-meter units, and then 60 meters, and then it had moved 20 meters, and then 30 meters. And then in time, it's like 30 minutes, hour, whatever it is. And then you get these deltas that you can then run a multi-layer perceptron on and get this continuous embedding of these changes for a single point. And then you can also get a representation of the features at that point. And then you basically do a dot product to figure out, okay, how does this feature relate to points that differ in space and time? And then what you end up with is a trajectory that kind of has this built-in representation of the space and time relations that we then pass to the rest of the model. So every time we get in this data, and there's a step where we have to compute these windows efficiently in real time. So we trained this model and we got some pretty decent offline results on human annotated data. It looked pretty good, but we know that the validation set we were able to collect is only a small portion of the real world distribution. So we really need to assess the model in that context to understand if our results are actually good enough for our users.
Yeah, I have a question. Do you have some intuition for why the continuous point embedding and 1D CNNs improve performance over just feeding in the longitude, latitude, timestamp, and other features directly to the transformer layers?
Yeah, so I think my intuition for it is it allows you to basically it gives the model a prior on the fact that it should be paying attention to the differences in space and time between the points, instead of assuming that the model will basically learn to care about that explicitly. So by having a kernel around each point where you are actually pre-computing the differences in space and time, and otherwise the model might be hard for it to know that it needs to use Haversine distance because you're on a sphere or something like that. It kind of shrinks what the model is going to have to learn a bit by providing those more explicitly. So what you're learning is just how do you use these representations and these differences, rather than that you need to be paying attention to it in the first place. Yeah.
One short follow-up question. Since you're using a windowed approach, but you're going for real-time predictions of this, how much does having to have a window of points affect what your prediction is? Because essentially, if you get one point in, then you have to use so many after, or if you're only considering the center point of the window, then you have to wait for so many points to appear before you make a prediction.
So what we actually do is we have we pad it at the end, so it's just zeros, and we tried a couple different ways of padding it, and actually it having zeros continuous after also kind of provides a marker to the model, an input that this is the end of the sequence. And because the model needs to learn, I want to predict what's at the end versus what's at some other point, that is a way that's consistent throughout the data of the data that's ending always has these ending zeros, whereas no other point in the sequence will have I don't know, the right side of its kernel still be zero. It's always going to increase in space and time in some way.
Thanks.
Cool. All right, so now we're going to talk about how we actually worked on getting this model to perform well in the real world. So the first step to doing this is get the model into the real world as soon as possible. And what this means for us is getting the outputs in the Skylight integration platform at a global scale. And so the Skylight integration platform is basically a staging environment where we're feeding in the real-time AIS streams to our models, but we're not showing it to users. It's behind a VPN, and it's basically allows like the Skylight team to see what users would see before actually shipping it to the users. Why do we want to do this? So the first reason is a global view of the outputs as a user would see it. Make sure that the assumptions we're making about the model's performance align with what a user would want. And so we can look at the data the way the user sees it. When we identify errors, it's over the whole distribution that a user would care about rather than just our validation set. And that's really, really useful. The other thing about getting it in early that's really important is we're able to, like as the Skylight team as a whole, we're able to work together for months before the model. We had enough data to actually train a good model, to actually get this model into a situation where we could produce real-time outputs because we were focused on getting it there from the beginning. So when the model was finally like ready to be tested in integration and for that iteration process to happen, we'd already done so much of the work that it would take to actually see these outputs at global scale and have it integrated into the rest of the system. So one of the things that seeing the outputs at global scale lets us do is identify different sources of errors. And there's kind of two ways we do this. So the first is when you have outputs at global scale, you can do pretty reasonable sampling over the globe. You can get stuff in different areas, and you can do this pretty quickly because you'll be able to run it for 2 days and get a bunch of outputs that you can then have experts annotate for either model evaluation to see if you should ship it or to create more validation sets to improve the performance. The second way, which is a really cool feature of AIS data, is there's actually a lot of patterns that like emerge without expert analysis that are like errors with the model to us just by looking at the global view. Like for example, in this photo, you can kind of see that some shipping lanes start appearing, and we know that vessels aren't fishing in shipping lanes. So that gives us a key of like, okay, that's an error we'd address. We can look at outputs near ports and stuff like this, where there might be like similar navigational movements, and we can see those specifically. And this basically lets us short circuit needing to like get expert evaluations and validation like over and over again as we improve the model. We can actually take these global views and then from these global views kind of get a pretty accurate heuristic understanding of like what the errors of the model are and target addressing those. So if we want to address these errors, we're going to need to go through these cycles of iteration where we basically identify the errors, we develop a strategy, we evaluate it, we ship it back to integration, we get all these results, and we kind of see how it looks. Some key points of friction that we ran into were first determining if a bad output is due to the model or a bug in another part of the pipeline, gathering and constructing targeted validation sets. If we want to make stepwise improvements over the model, we need to be able to create validation sets that focus on like this source of false positives or that source of false positives, so we can make sure that we're making consistent improvement towards having a high performance model. Also, when you have such a large distribution that has like really long tails of behavior, our validation sets are never going to be completely comprehensive. So we need to be able to prevent partial regressions over stuff that we might have been doing well on, but not measuring well, and is only really obvious maybe at a global view, or for things like recall where we can't really get a good ground truth number of like how many boats are actually fishing right now. Yeah, the other points of friction were it obviously takes annotator time to build data sets. So we want to do things like using these global views to get feedback so we don't actually have to wait for that. And also we need to make sure that it's really easy to ship new models so that we don't get stuck like passing it over to someone else, which is very configurable and easy to do. So how did we do this? Basically 2 ways. We focused on building tools that made these steps really easy. So we had like a debug endpoint that let us assess like, okay, we have this output in like integration. Let's go grab the data that was for it, be able to rerun the model, be able to modify that data, inspect that data, and see like, okay, where's the bug coming from? Basically being able to write queries for like across the outputs in a variety of different ways, like looking for stuff in a specific area at specific speeds, whatever it is, and either be able to, in some cases it'll be obvious like, oh, these are all mistakes that should have the same label class, and we can create validation sets that way, or we'll pass them off to expert annotators to get them validated. And the last one is this tool called distribution delta analyzer, which I will talk about in more depth, but basically allows us to prevent against partial regressions and figure out how the models are going to change without actually having to annotate a ton of data. And then the last point is following a lot of machine learning specific CI/CD practices that allow us to make sure our model's consistently improving and that it's maintainable and all these other fundamental software development principles. Cool. So what this distribution delta analyzer allows us to do is it allows us to basically, we had a model in our integration environment, so it's getting real world inputs and producing outputs across the globe. We want to be able to say like, okay, we got all these outputs over this time period. We have this new model and we have pretty good offline performance with it. We want to be able to see, okay, would it actually have good performance across the whole world, right? And we don't really have ground truth across the whole world of like, okay, are all these outputs actually good? But what we can do is we can pull all the data that model like went over the past like week, whatever it was, and run the new model against it and produce a confusion matrix that shows the difference in the outputs. So one thing this allowed us to do specifically is at one point we had a model that seemed to have like improved offline performance and improved false positives. But when we ran this test, we found that there was actually a huge global reduction in phishing recall. So you can see here that the integration model thought all this stuff was phishing, but the new model only thought a small fraction of it was phishing. And so this shows us that even though we had good offline performance, this would have caused a huge regression in terms of recall for our users. And we were able to do this analysis without actually having to like put the model in integration and wait a couple days to figure it out. Another way we can use this tool is, let's say there's a small difference between the two models and we want to get an understanding of like, okay, we have this better offline performance and there's a small difference. We can say like, okay, do the changes match our intuition of what should happen? Let's say the idea is like, okay, we want to reduce false positives where we think it's transiting or we think it's phishing, but it's actually transiting for the sun subset. If we see the distribution shifting in that direction, that might be a good indication that, yeah, like our plan actually did work and it's worth trying an integration and seeing what the outputs were. Another thing we can do is we can sample specifically from the differences and either get experts to validate them and annotate them, or we can like create a visual mosaic of these and look at a bunch of them and see if we can get a sense of like, okay, are these regressions or is it just kind of disagreeing in the way we want to, or in some like trivial way where it's like really hard cases that sometimes it gets it right, sometimes it gets it wrong, and it's pretty 50-50 or something on who's right. So this is kind of just a not exhaustive list of everything else that we did to effectively ship this model. Some things I want to call out is that's very machine learning specific is we ensured that our code for training and inference like shared all the same core components. We didn't have like separate training code base and inference code base. It was one single code base that was built to be in production from the start. So it makes it very easy to go, let's say from like, okay, this is our model in production. We want to recreate it and retrain it. That's very easy, and put it back into production. Those steps are very simple. There's not really a handoff for a translation there. And like components such as like a preprocessor, which might like clean and normalize data, that's going to be shared throughout both training and inference. So there's not any type of divergence that is possible where maybe you're normalizing slightly different during training and inference, and that creates this like weird disconnect between what you're seeing in training and the outputs you're seeing in inference. Yeah, cool. So this is kind of just a very high level overview of what our deployment architecture actually looked like. We ran the entity classifier offline at a regular cadence. So basically at every so often, after like an initial big push of saying like, okay, for all the stuff we have sufficient historical data for, let's go classify it. Let's say, is it a buoy? Is it a vessel? Put that in the database. And then every so often it's like, oh, did we get any new stuff that we haven't classified yet? And then we add that to the database. And then basically what happens is as we get this stream of new data, we check, okay, is it a buoy or is it a vessel before we pass it to the activity classifier, which is going to create phishing events in the Skylight UI. So after these iteration loops that included many different things, such as like mining portions of the data set for additional false positives and various post-processing and thresholding and figuring out, okay, how can we threshold these model outputs to align with what we want for users. After 2 expert evaluation loops, which are specifically focused on answering the question, is this good enough to ship? We were able to improve the accuracy from 44% to 71%, and while maintaining really high quality global recall. That's something that we don't have quantitative numbers of what that should look like, but we can have experts look at the global map and different regional based folks look at the map and say like, okay, are we seeing what we expect for this time of year in this area, and make sure we're not missing anything super critical. So an important thing to mention to put this kind of into context is Skylight had a previous model that instead of doing real-time prediction, it would wait till like 6+ hours after the event and kind of go back and say, okay, did phishing happen at any point during this time period? And those events had about a 50% accuracy. So 50% of the time we were saying it was phishing when it was actually one. In that paradigm, in this paradigm, we're actually taking in a lot less input information because we're only seeing what happened up to the point where we're making the prediction. And then we're saying it's phishing or not. So we're able to see this improvement on a harder task. Yeah, and then another huge impact of this is we now have real-time AIS events. That was not something that our users had access to. They had no way of saying, okay, what's phishing and what's happening right now. And that's a really, really cool thing to do. And our part of the pipeline is kind of a small bit of the latency. A lot of it is the downlinking time and some other details of like how long you need to wait after you get a message to make sure you get like something coherent. Yeah, so I guess at this point, it'd be cool to go look at Skylight and see where people are fishing right now. So this is today. This is where people are fishing. We can go to the coast of Australia and we can, it loads. Oh, that one didn't load. That's awkward.
Sorry, you gotta love live demos.
Yeah.
I like the confidence. This is good.
Yeah, I'm confident in the outcome.
Yeah. If we can see the results, the model was right.
Yeah. So we can look at.
Just give it.
Yeah. So this is it seems like a Chinese vessel fishing off the coast of Senegal, and that's pretty cool to see.
Can you just pause there?
Yeah. One thing that Skylight does not do is we do not decide what is illegal and what's not. That is kind of way beyond our scope and not like a scalable thing to try to do. So it's up to the people in this region to look at their waters and be like, okay, did we make an agreement with these Chinese vessels that they're actually allowed to fish there, or did we not? And that's kind of would be an endless bag of worms for us to try to figure out like, okay, who, when, what year is allowed to fish where and stuff like that. So we just provide the information so people can actually make the decision. And one thing you can see on the Skylight map to make this one interesting is, so this line right here is the exclusive economic zone. So this vessel would not be able to like a priori fish in this area unless the country whose economic zone it was let them. So if they weren't allowed, it would be a potentially interesting case. And if not, there's probably some restrictions on what part of the year, when should they be fishing. So the governments of this country will be able to assess and figure that out. Cool. Yeah, people who want Skylight accounts or can get them and want to like click around and stuff like that, please ask. Always happy to talk about it and look at it and get feedback. Cool. So there are still a lot of rooms for improvement for this model. It has about 70 to 80% accuracy right now. Just to put that in context, the IAA, when we had like, okay, we have a bunch of events, we want to say like, is phishing happening right now? Experts agreed on that about 85% of the time. So even at an expert levels, there's still not 100% confidence. And yeah, we still make a bunch of mistakes and we want to listen to feedback, consistently improve and not make those mistakes again. This is an example of 2 false positives that we see right now. On the left, you have a firefighting vessel doing this like really complicated movement pattern. And then we have a tugboat on the right doing this other pretty complicated movement pattern. And some of those still pop up, right? Like we're able to filter a good amount of like these other weird non-fishing stuff out, but you're still going to get some of those outputs that make it through the pipeline just because of the sheer amount of data going through. Your model's all like, we don't know exactly what is tipping this to fishing versus transiting or something else, but we do have ways to go and improve this. A very simple way is just getting better base vessel metadata. So if we can do a better job of integrating like what are like prior knowledge on like what vessels are, less of these vessels that are like currently unknown and required like me to do like extra research to figure out what type of vessel they are. If that's already integrated into the platform, it'll be easier to just filter out these errors a priori. Also, we can train models to do this task as well of like figuring out what type of vessel it is, and we can kind of integrate that into the pipeline as well to try to overcome this error. Yeah, so as Patrick mentioned at the beginning, these techniques for GPS modeling, while they're used for this AIS data, they're pretty agnostic to it being AIS versus some other GPS data. So specifically, like different regions have this thing called VMS data, which is very similar to AIS, but only available to the specific region. So for example, in Indonesia, they have VMS data that shows vessel movement in their waters. It's only to them. We don't have access to it. When we met with them a couple of weeks ago, they expressed interest in basically fine-tuning our model for their region's VMS data and applying it there so they can get more information about what's happening in their water. A second thing that we'd like to use these models for is doing human-wildlife conflict risk prediction with Earth Ranger. Earth Ranger has this really amazing data source of basically elephant GPS movements. And so elephants, as they're pretty intelligent creatures, they do pretty interesting things just before deciding to like go rush onto like farmland or something like that and cause harm for the elephant and the farmers. And if we're able to kind of anticipate those before they happen, we'll be able to prevent those conflicts. That's still very, very early stages, but we're really excited about the opportunity to get to do that. Also, there's a lot of other AIS-based tasks that Skylight might want. And at this point, it's a lot of just, okay, let's pick the task, let's get some labels, and then plug it back into the model. We don't really need to design anything super different for it. Cool. So I want to highlight this is a massive team effort. I highlighted Josh, who is the lead software engineer. I asked him if I could put his face really big, but he did a humongous amount of work and spent so much time like working with me, making the long commute to the office to actually like sit and talk with me and work with me on this project so that like our model would work effectively in production. And it was really great to work together on this. And I want to give him a ton of credit for all the amazing stuff he did. Yeah, also Beaker was totally a huge part of the success of this. Beaker is very enjoyable to use and enabled us to do a lot of things really easily that like really helped us figure out what's the best way to model this, what different data combinations we want to try, and made it really easy to do that. And then I kind of added photos of the rest of the Skylight team, everyone from like project management to machine learning to product management to like the annotation team. That was such a huge effort. Also, SI helped us with this a bunch, and they were super instrumental in making sure that annotation project was effective, which if you want to hear more about the challenges of managing experts for a difficult annotation task, I'm happy to talk about it. Didn't want to bore you with those details today. Cool. Yeah, so that's it. Thank you. Now time for questions. Talk about anything. There's a lot of other details that we can go into if you want to hear more about the deployment, other stuff like that. I can do that. I just wanted to kind of start here and then we can dive in if people are interested.
A quick question about your distribution delta. I mean, the tool for regressions right now, but in terms of the, you had a couple ones where it was pretty stark. Was there any benefit to getting some kind of ensemble in terms of if you got improvements in certain behavioral classification? Like really, some of them are, I mean, I didn't realize it was that stark, but if they were that good in a number of them, or a priori you knew that the analyst was only interested in, I don't know, certain behaviors, right? Where you could basically get the benefits of that model versus a blanket or global regression rejection.
Yeah.
You know what I mean? Where, I mean, it's more work, it's more complexity and all that, but it seems, I didn't realize some of them were that stark in terms of if you were looking at, you know, certain behaviors and didn't care about others, it's like some of that goodness seems to get globally trashed in terms of like it's just thrown away.
Yeah.
Versus using, I don't know if ensemble or weighted ensemble would be the way, but some other mechanism either to partition the space or partition the inference space or something like that, you know, where
Yeah.
you could get the benefit of the model, but diminish the global impact on some of the other behavioral classification that like is bogus or, you know, just basically falls apart.
Yeah. So I guess I have two things to say for that. So the first is like the reason like you might get some things like this is that from a user perspective, they have preferences of like they'll be really upset if they see like a drop off in recall.
Yeah.
So we're paying a lot of attention to that in addition to like what the offline validation performance is. And so right now we've kind of maintained we're going to have one global model. It's easier to maintain. We can do that kind of stuff. But totally having an ensemble like will like pretty much anytime you ensemble models, you'll bump performance by like some percent. And that is something we can totally do. We just haven't prioritized doing it yet. There's certain deltas.
There is benefit to that, but even with recall, right? Even with recall, I could easily see a case where the global north versus the global south have totally different recall benefit. I mean, you know, one side I can see would want epic, just really, really good recall. The other one, like, screw that.
Yeah.
We that's not what we're looking for. We have a different motivation for using this tool. I mean, Nam and some of the program folks would understand that better, but I was shocked in terms of depending on your motivation, some people dial the recall thing all the way down and others want to crank it. I mean, they want to really crank it up and like, you know, so that was another, it makes the UI complicated.
Right? Yeah. The simplest way for us to do that is a lot of the ways we address those preferences.
Yeah.
Like obviously it's somewhat due to model, but a lot of it's due to how we post-process the data. How do we feel confidence? Are there specific areas where we either like limit or don't limit whether we're actually going to say we know what it is? And that's strongly based on user preferences. So we would have to have like two different parts of that where it's like we would have to route it based on lat or long of like which one it goes. And then you'd have to have some clearly definable user partition, and then we'd have to have a strong stance on like, okay, we're not doing this in more than 3 different ways, because it's very easy at that point for then every country to be like, oh, but we like this, we like that, and that's not a rabbit hole we're going to go down. Yeah, Oliver.
How useful to users would it be to be able to distinguish between different like fishing techniques, different types of fishing, and is that something you could do?
Yeah. So that's I think on the roadmap soon for Skylight, and it is useful. I think that it's a lot of the time if you show them the fishing event, they can tell or they know what's in their waters. So it's not like as important. The big user problem that this is solving is like you have this huge deluge of information. They need to know what they actually want to look at. Once they're looking at it, like they'll be able to tell. There's obviously cases where if like you have an analyst that doesn't have a ton of expertise about this, they might not be able to tell. So it would be helpful to do that. But in my mind, that model will be kind of trivial. Not trivial, but that might be a little strong. But it'll be easier because you're already limiting it to stuff that's only fishing. You don't have to deal with all this other behaviors. And there is like, at least between most of the gear types, some pretty distinct things. I think Nam wants to add something.
No, I totally agree with what you're saying, Henry. I'm super excited for like all the additions we can do now that we have this foundation set. But I just wanted to mention, like, for context for those that haven't worked so much with Skylight, we have a really targeted user base of enforcement and compliance users. So that's why, to what Henry's saying, like they kind of, to some extent, already know what sorts of activities to expect in their area. But if we had a wider audience, like a wider community of scientists, researchers, journalists, then yes, like they won't know different gear types, different types of fishing, and the value of doing work like that would become even more valuable. But I just wanted to share that context.
Does your model include like absolute position information or just like relative information?
Yeah. So the main way we tried including so we tried absolute position information in 2 ways. First, we just passed in like basically like a lat long directly. There's some other details, but that actually like made the model less generalizable, and it made like the transition from training and like offline inference to real distribution have like much bigger shifts than when we left that out. The second way, which we will likely add back in soon, is doing basically just providing like an extra feature that is like distance to coast, like how far are you away from shore. The problem with that is it's useful, but it was super coarse resolution previously, so it wasn't really providing strong enough signals, and particularly like in island areas around fishing, like it would think the vessel's almost on land when it's actually not, and things like this. Luckily, Patrick's done some really cool work of making like the highest resolution distance to coast map in the world. So basically it's 10-meter, it'll be 10-meter resolution. So you can very clearly like say like, okay, this is fishing near islands. It's not actually on an island. And then that feature I think will be super useful and provide us a lot more information in that case.
Yeah, Jordan.
Yeah, Henry, you talk about the challenges of building these models, you know, annotation, et cetera, right? Can you share about the uniqueness of the data and how helpful that was helpful for you all building these models? I'm just curious, like from the standpoint of having AI, all these AIS messages, right? Billions. How helpful was that in building the model, generally speaking?
I'm not sure I really understand your question, so just give me feedback if I'm going in the wrong direction. I mean, like, yeah, obviously this wouldn't have been possible if we didn't have a lot of data. If we couldn't like, I don't know, pass in a lot of outputs, get a lot of outputs quickly, test the model across the globe. Even if we weren't able to label it, the fact that we were able to like, I don't know, like I can run batch inference over like a year of data and get all the outputs that the model would say for a year if I wanted to, and things like this. And that's really helpful in analysis. And it also leaves a ton of room to explore stuff like self-supervision and stuff like that, which we like didn't focus on here because the goal is to ship a performant model initially, though I think that those techniques could really help and improve the performance. Our mind though is like, okay, that's something we do after, once we have something that works, that we can then kind of plug and play with and see what the performance is. So yeah, it wouldn't have been possible to do this well without like a big data set.
I want to add a few things. So in comparison to NLP, there's, as you might imagine, quite a bit less work, right, on GPS in general. But because it's transformer based, and obviously that's kind of the state of the art for this kind of data, we could borrow a lot from NLP. Unlike an NLP, the input data here is already vectorized, right? Like we're already in a space that is amenable to, you know, as input. We don't have to necessarily do like a vector embedding like you do in language. But also, unlike an NLP, there's huge variability between, like huge variability in the intervals between successive tokens, right? So like in language, the white space between words is fixed, right? It's not like super meaningful typically. In this space, that's not true. And that's a huge problem. And historically, it's been difficult to address. People interpolate, they do all kinds of things that are not great. And so there are areas, there isn't like an off the shelf necessarily like model that you can just immediately apply to this data. So so there is an opportunity there. I'm not sure if that's what you're referring to, Jordan. That's kind of unique to AIS or GPS data. But there's a lot we could borrow from the NLP world. Like, thankfully, there are tons of research groups, you know, pushing the state of the art in transformers, and obviously we borrowed heavily from that.
Yeah.
Oh, this is great. Thank you.
Yeah, kind of adding one more thing onto that is that like a lot of the interesting stuff is like, how do you pick relevant data if you were going to do like large scale self-supervision? Like there's a lot of stuff that has a lot of redundancy. Like you need to make sure that you're not training on a huge amount of vessel just going straight or vessel just staying in the same place. You need to create like a data curriculum that's going to be actually interesting to train a model on and be a good use of your resources. So that's something that I'm excited to explore if I have time. And happy to talk about with anyone if they're curious. Yellen.
Yeah, I think besides the performance, another very impressive aspect of this project is the low latency. So could you explain something like what's the aspect that contribute to this like latency?
Yeah, I think I have the slide for that somewhere. All right, yeah, so this is kind of a slightly more zoomed in view of how this works. And so there's kind of two main things we do to maintain good latency. The first thing goes back to the point I was making about every new message not necessarily providing new information. So we don't actually do run classification every time we get a new message. We basically have a high recall, low precision, super simple statistics-based model of like, is it even possible that there's a new activity? Right? So like vessels in the same place, or vessel going straight at same speed, like we don't repredict what's happening. We try to basically only predict if it may be changed, then we run a prediction. So that's the first way we deal with the latency issue, by just predicting less often when it would be redundant and unneeded to do so. And then the second way is basically just making sure that the activity pipeline of like passing in this data and creating the predictions is efficient. So what we do is we basically have three different components of the model. We have a preprocessor, a model, and a post-processor, which does the thresholding and all that kind of configuration. And the main way we got this to be performant is we deployed it in such a way where we could scale each of these components to different resources separately. So we could allocate a ton of CPUs to do the preprocessor and then only GPUs for the model. And the model would basically have this batching proxy that goes and says, okay, how many examples are ready in like, I don't know, 10 milliseconds, 20 milliseconds, and it grabs however many are ready at that point, puts them in a batch and processes them in parallel, and then passes it to the post processor. This basically means that our models are always taking as much data as they can in that time, and that we can make sure that the models are saturated and don't have to wait for enough pre-processing data to be available. Yeah.
I was interested in the debug endpoint that you talked about before, and how you determine whether a bug is caused by the model or some issue with the pre-processing step.
Yeah.
Talk more.
Yeah. So I guess I think it's like a generally thing that you should have as a sanity check in any machine learning thing of like, okay, if you're producing an output for users, you need to be able to trace that back, just like any other software engineering thing you're doing. And the way this helps you figure it out is it pulls the data in the same way that the model would see it in production. And there's actually quite a bit of nuance there in this case, due to the fact that like the data that we think is available at a certain time step when we did prediction is different than the data that was available before it at this point in time when we're doing our debugging, because oftentimes like you might get some backfills of data due to how the downlinking actually shares the messages, and we'll get some stuff out of order. So if you're just like grab all the messages before this point, you'll get different inputs than if you grab it in the way that it got it at that time. So like one example of how we use this tool to figure something out is that like at some point we were getting a bunch of really weird like transiting outputs, and we were like, oh, why is this happening? What is the reason? And because we were able to run this pipeline and pull the data, we were like, okay, first check, is it still doing the same thing that we thought? When we get the data, are we reproducing the outputs we see in production? We're like, yes, okay, then what should it be? So then the next step is kind of like inspect the input data and figure out what's happening. And we figured out that we're actually like in the past 3 months, we were passing the first 2,000 messages in that period instead of the last 2,000. So the model was predicting on data from like a month ago instead of right now. But the UI was still showing like what it was doing currently. So when we looked at the UI, we saw a very different like output class and behavior than what was actually being put in the model. And that let us know like, oh, we shouldn't be trying to like think of model related ways to fix this. We should just go fix what we messed up in the data pipeline.
Well, let's call it. So everyone, so the model is going to get open source, and well, everything is actually getting open source and will be available on, except for the data. So the model is going to get open source and it's going to be available on GitHub. We're writing the paper now. It's going to get published on arXiv very soon on this talk. And thank you everyone for joining. Thank you, Henry. And please let us know if you have any feedback.